Okay, here we'll take a look at how to calculate some of the potential generated by some of the charge distribution. So this one, the charge this. So actually, in chapter 22, we have already seen this structure before. Okay, actually at that time we tried to calculate the E field for this along the z-axis. Okay, so here we will try to do the similar thing. Okay, but you feel that calculate the potential for this structure along the z-axis is easier than to calculate the E field. Okay, because the E field is a vector field, so you need to do some decomposition. So it involves some trigonometry function like cosine of theta or something like that, or sine of theta, something like that. Okay. So here with a charge disk, also in the figure, consider differential element consisting a flat ring of radius r prime. Okay, so which means that the full disk here with a radius capital R. Okay, so similar as what we did in the chapter 22, we try to separate this disk into many different rings with different radius from 0 to capital R. So when we try to pick out one of it, we call the radius of a ring is R prime. Okay, so actually on each of the R prime we have dq okay, so we have the surface charge density, okay, multiplied by the area of the ring. Okay, area of the ring. So the area of the ring, what is the area of the ring? We try to use a scissors to cut it out and then to try to flatten it. Okay, hopefully become a rectangle. Yeah, although it's hard to imagine, but try to believe it is true. So actually, if you try to cut it out and then try to flatten it and then approximate it to be a rectangle, the height here will be here, which is dr prime. Okay, and then this is actually a circle. So when you try to flatten it out, the width of this rectangle, will be the circumference of the circle, which is 2 pi r prime. 2 pi r prime. Okay, so which means that the area here, so the area dA here will be 2 pi r prime dr prime. Okay, so which is this one. Okay, so which means that this one actually is dA. Okay, so sigma times dA will be the charge on that part. Okay, so actually we want to find the dV. Okay, dV. Okay. dV here generate the potential at that point P, okay, generated by this ring. Okay, so the good news is the distance from this point P to the whole ring with a constant distance. Okay, suppose after fixing the radius of a ring, okay, which means that the distance is r. So r is square root of z squared plus r prime square. Okay, so this is fine. Okay, so what we really have here is r is z squared plus or r squared equals z squared plus r prime square. Okay, so which means that we have a dv k dq over r. Okay, so this is what we get before, and we try to plug in dq to here, so we have a sigma 2 pi r prime dr prime. Okay, so from here to here, and then this is k, and then finally r is square root of this stuff. Okay, square root of z squared plus actually r prime square. Okay, so we have a prime there. So so to find the whole overall potential at this point will be V equals integration of dV, okay, from 0 to I think it should be capital R rather than capital L. Okay, so it should be like that. Okay, so here what we get is we can actually cancel this pi with this pi, cancel this 2 partly with this 4, down to a 2. Okay, so here we have a 2 epsilon naught placing here, sigma placing in the front. Okay, so these are independent to d r prime, to r prime I mean. Okay, so the remaining stuff r prime, d r prime, and then square root of c squared plus r squared. Okay, so hopefully this integration is easier to work out because we can have the chain rule, which means that r prime, okay, r prime dr prime will be d r prime square plus c square, okay, over 2, something like that, something like that. Yeah, so this is also r prime here. Okay, so actually after getting this part here, okay, so we can actually integrating this part. Okay, this is a negative 1/2 power, so integrating that will be something like going to the top. Okay, this stuff going to the top with a half square, I mean half power. Okay, and then divide by 1/2, so that cancel this 1/2. Okay, so which means that we try to, okay, so this stuff is like this stuff of integration of r prime dr prime over square root of c squared plus r prime square will be like c squared plus r prime square, okay, to the 1/2 power evaluate from 0 to capital R. Okay, so which means r prime to be r, so we have a c squared plus r squared square root here, minus plugging r prime to be 0, so we have a c squared, take the square root to be minus c, okay, like this. Okay, so this is pretty easy to work out. Okay, so at least, okay, of course it need to work out some integration, but at least, at the very least, it is easier than calculating E field with the same structure, exactly the same structure. Okay, and actually we can get this expression. Okay, so here, okay, here, what do we do with this potential? Okay, so the idea here is we can actually calculate the field, which means the E field from the potential. Okay, after getting the potential along an axis, okay, we can really know the E field, or at least of that component along that axis. Okay. Okay, so here what we try to see is, suppose we have a positive test charge Q0, which is this one, and then actually move through a displacement ds from one equipotential surface to the adjacent adjacent surface. So the work the E field does on the test charge during the move is negative QV. Okay, negative QV. This is the work done. Okay, because this is E field. Okay, this is E field, and then okay, actually it will do some work. Okay, so actually the work, okay, in another form is like the force dotted with the displacement. The force dotted with the displacement is one form to express the work done. Okay, so this is the work done. Okay, another way to express the work done is this is, okay, so this will be F equals QE. Okay, so this is a Coulomb's force. Okay, the definition of the E field. So F equals Q0E. Okay, dotted with ds. Okay, so this is the work done in one way. Okay, so the other way is this negative Q0 dV. Okay, so W equals negative delta U. Okay, if you still remember. If you still remember that W equals negative delta U, okay, delta U. which is negative Q0 delta V. Okay, dV is delta V. Okay, so actually like this. So we have W to be this one and also this one. So they equal to each other. So we have negative Q0 dV equals Q0 E cosine theta ds. Okay, so they don't necessarily point to the same direction. So we assume the angle between the E field and the ds is theta in radian. Okay, so in that case we can cancel something. Okay, can actually cancel the test charge. Okay, as always, yeah, because the amount of the test charge shouldn't be related to what we want to know. Okay, so finally what we really get is this E cosine of theta here. Okay, and then ds move it to the other side. Okay, so here we have a negative dV. So finally we have a negative dV over ds on one side. Okay, so the good thing for the Leibniz notation of the derivative is this derivative act like a division. Okay, act like a division. Okay, so which means that you can see like, okay, so this is one thing and then divided by this stuff. Okay, so it turns out to be a derivative. Okay, so finally, okay, E cosine of theta, we can actually call it the component. Okay, the E field along the x-axis. Okay, so we don't need to care about what is the x-axis. Okay, it can be one of the axes in the 3D space. Okay, so it don't really matter whether it is the x-axis, y-axis, or z-axis, or actually one axis in between. Okay, so the idea here is like suppose this is an arbitrary axis. Okay, s-axis. Okay, so actually the E field actually points to some other direction. Okay, so actually the angle between them is theta, so which means that this is actually the ES. Okay, this is actually the ES along the s-axis. So this is the s-axis component. Okay. Well, so here we come up with a conclusion that, okay, so the potential, actually a scalar field, is actually related to the E field along the axis. Okay, suppose we only need to know the potential along that axis, then we just need to take the derivative with respect to the axis coordinate and then take a minus sign, then we will know the E field along that axis. So how can we do this? How can we make use of it, of this formula? So before using that, let's try to generalize this expression. Okay, so actually here we have s-axis. Okay, so why not making it Ex is okay, Ey is okay, Ez is okay. So Ex will be negative dV dx, Ey will be negative dV dy, Ez will be negative dV dc. Okay, so actually all these V are the same. Okay, so because V is a scalar, it don't have any axis component. Okay, it's scalar field. Okay, but actually it is related to the E field, which is a vector field. Okay, so suppose in a Cartesian coordinate we have x-axis, y-axis, z-axis component. Maybe some of the axis may be zero, but anyway, okay. Suppose if we would be able to know the v in terms of x, y, or z. Okay, so v can be a function of x, y, and z. So in that case, take the derivative with respect to x, to y, to z, then we will know the ex, ey, ez. Okay, then finally, after knowing all the components of the E field in the x, y, z axis, okay, we will actually know the full E field. Okay, and actually in the mathematics, okay, we have another notation using the upside down triangle to represent this three-dimensional or high-dimensional derivative. Okay, so for one-dimensional derivative, we usually will use the d, or actually we sometimes will use the more correct to use the to the notation like this, okay. And this I usually we call it round, okay. Don't know why, okay, but usually call it round v round x, okay. dv dx is for ordinary derivative, okay. So 叫做常微分 ，okay. 第一是常微分 ，OK， OK 这个叫做partial derivative 偏微分 ，OK， so partial derivative, okay, or the other one also like partial v or round v round x or partial v partial x, okay, or partial v partial y here, negative partial v partial z here, okay. So actually, we have three independent formulas here. Okay, so for the x-axis, y-axis, z-axis. Why not making it one? Okay, so the idea here is like, okay, the E field, the whole E field is actually negative gradient v. Okay, so gradient is an so-called an gradient operator. This is so-called the gradient operator operator. 叫做梯度的算符算符 ，OK， actually this gradient in Cartesian coordinate, okay, in Cartesian coordinate will be like partial x I hat plus partial y j hat plus partial z k hat. Okay, so this is an operator. Okay, it cannot be exist by itself. It need to operate to something behind it. Okay, so actually this is a gradient, so-called the gradient operator. The gradient operator. Okay, so which is like we would like to do the partial derivative to something behind. Okay, so actually this gradient operator can operate to a scalar field, okay, to generate a vector field, okay, which is like generating the E field from the potential, from the electric potential using this gradient operator, but taking a negative sign, okay. So you can feel that, okay, so actually the E field can be also written as Ex I hat plus Ey j hat plus Ez k hat, okay. So after using this expression, okay, which is like this one like multiply by this one, okay, and then you distribute, you have totally 9 terms, but only I dot I, j dot j, k dot k will be 1. Okay, other terms turns out to be 0. So turns out to be like which means that a gradient v can be expressed as a partial v partial x I hat let me see. Yeah. Oh no. Okay, this is not E here. Okay, this is not E here. It should be like, okay. It should be like, okay. I'm a little bit confused. It should be like, okay. It should be like this. Okay, it should be like this. Okay. Gradient v should be like this. Okay, so it'd be like partial v partial x I hat plus partial v partial y j hat plus partial v partial z k hat. Okay, after applying these to the v, okay, you don't have I mix it up. It should be, yeah, that one I just mentioned is like a gradient dot e. Okay, should be another stuff, okay, related to the Gauss law, okay, the differential form of the Gauss law, okay, is this one. Yeah, but we will talk about that later on, okay. So this one is taking the gradient to the the potential. Okay, turns out to be like this. Okay, and then here if negative partial v partial x is e. Okay, so if we have a negative sign in the front, okay, so we have a negative, then this one is negative, this one is negative. Okay, so this one is ex, this one is okay. Together with this one is ey, and then this one is ez. Okay, so finally turns out this one to be the vector e. Okay, so this is the just a notation. Okay, just let you know. Okay, we have this kind of gradient in the Cartesian coordinate. If it is in cylindrical coordinate or spherical coordinate, okay, the expression will look strange. Okay, if you're interested, you can try to check it out, the gradient operator. Okay, but here we can slightly talk about this so-called the gradient theorem. Okay, actually in calculus class you also learn something called the fundamental theorem of calculus. Okay, which is like suppose you know let's say the fundamental theorem of calculus. Okay, so actually this gradient theorem is also a high-dimensional fundamental theorem of calculus. Okay, so for the one-dimensional fundamental theorem of calculus should be like suppose we have f of x, okay, to be the df of x, okay, dx. Okay, suppose we have this is the derivative. Okay, you know, okay, integration of f of x dx from a to b should be f of b f of minus f of a. Okay, so they are inverse. Okay, they are inverse operation to each other. Okay, so this is called the fundamental theorem of calculus because they are invented by two different paths. Okay, for the derivative, as you learn the calculus, it should come from the limit. Okay, you try to change the x-axis a little bit, so the function will also change a little bit. So this ratio, we call it the derivative. But for the integration, the definite integral actually comes from the Riemann sum. Okay, you try to have something like this. Okay, you try to know the area, so that you try to cut it into many rectangle, and then try to add all the area of rectangle together to be the whole area, which is the original definition of the definite integral. Okay, but it's somehow like they are totally different. Okay, so they are totally different. Okay, so this is the derivative. This is the derivative. df dx. Okay, so this is like integration of f of x dx from a to b. Okay, so they are, so from the definition itself it looks like they are irrelevant to each other, but actually the fundamental theorem of calculus tells you that they are actually the same. So you can do the integration not by working on the Riemann sum. Okay, you can just find the antiderivative and then plug in the lower and upper bound, and then that's it. So here is the gradient theorem. It's like can go to higher dimension, which is like suppose we have a scalar. Okay, we have a scalar function. Okay, and then we can just take the gradient. Okay, turns out to be integration. Turns out to be an integration. Okay, so so this is a generalized case of the one-dimensional fundamental theorem of calculus. Of course it's a little bit out of the scope of this course, but just let you know if you are interested in the mathematics behind. Okay, so simply speaking, what can we do with this, or at very least this one? Okay, or maybe if you feel like this upside down triangle is too horrible. Okay, actually we can make use of the upper three formulas. Okay, so just now what we already get is this formula from this graph. Okay, we can we can know that, okay, we know that calculating the potential of this structure is easier than calculating the E field than this for the same structure, okay, at least for this structure, okay. So can we come up with the E field with this expression? Okay, so the idea is we can just take the derivative, so which means that Ez of this one will be like the partial negative partial V partial Z, okay, or dVdC, or at very least this one is only related to C, not related to X, Y, okay, so this is only a function of Z, okay, so actually you can actually write it as a dVdC. Anyway, we can actually write it as, okay, so this stuff is a constant to C, so negative sigma over 2 epsilon naught, and then we have a dz, and then we have a square root of the C squared plus R squared minus Z. Okay, so take the derivative, negative sigma over 2 epsilon naught. This is this stuff to the 1/2 power, so turns out to be square root of C squared plus R squared to the, so you need to multiply by 1/2, but you have the chain rule, okay, you have the chain rule. You take the derivative of the inner function, so which is C squared plus R squared. So taking the derivative with respect to C will be 2Z, okay, 2Z. And then finally minus, okay, the derivative of Z is easy, which is nothing but 1. Okay, like this. Okay, so finally we can distribute this negative sign inside. So finally it turns out to be sigma 2 epsilon naught, and then 1 minus this, 2 and 2 cancel, so Z minus Z over square root of the C squared plus R squared. Okay, so actually this one is the same as this one. Okay, so for this one you don't need to know the potential, you don't need to know how is the relationship between the potential and the E field, but you need to work on this integration. Okay, so it is at least more complicated to calculate. You need to decompose the component of the E field generated by each of the ring, and then cancel some of the components, something like that. Here, the idea is electric potential is another tool, so that it is easier to calculate because it is a scalar field. And then finally, we can work on this derivative. Okay, as much as you have learned the calculus, you know, for most of the case, calculating derivative is easier than calculating an integral. Okay, so some of the function, the integral is not analytical. Okay, some function, okay, is not integratable, but for nearly all the function, it is differentiable. Okay, so this is the point here. Okay, so here this next topic is the energy, the potential energy. Okay, of course it is related to the electric potential. Okay, so electric potential is what we call a potential, is a voltage. Okay, it's a voltage. Potential energy is an energy. Okay, so they are related but not quite the same. So electric potential energy of a system of charged particles is equal to the work needed to assemble the system with particles initially at rest and infinite distance from each other. Okay, so which means that originally all the charge you try to put it in finite far away, so that this whole system don't have any potential energy stored there. Okay, so here after that you try to pick it one by one to the distance, to the position wherever you want for each of the charge. So after doing that, okay, so for example, if we have only 2 particles, placing the first one you don't need to do any work, okay, because there's no other E field in the space. Okay, so there will be no force acting on this charge. So if you try to move that charge into a position, okay, without the other one, okay, then you don't need to do any work. There's no potential energy stored there. But after you, but when you try to put the other one, okay, close together, let's say they have a distance r, okay, so energy is also a scalar variable, so that you don't need to care about the direction. So we only need to consider distance between them. So U will be like K times QE over Q1, Q2 over R. Okay, so related to the charge of the two charges, the charge amount of the two charges. Okay, and then also the distance. Okay, so but here in the denominator we don't have R square comparing to the Coulomb's force. Okay, so far we have learned four. Okay, formula with similar structure. Sometimes the denominator with R, sometimes with R square, and then for the numerator, sometimes Q1, Q2, sometimes with only a Q. Okay, but later on I will just try to summarize it a bit so that hopefully you will not mix them up. Okay, but the lower case is that if the total energy of a system of particles is the sum of potential energy of every pair of particles in the system. So which means here we have more than two. Okay, so if we would like to also calculate the potential energy, okay, potential energy stored in this system with multiple charges. Okay, we need to use this formula. Okay, so the first one is also the K, and then the remaining terms we try to add something together. Okay, here is Q1, Q2 over R. So here we try to denote it as a Qi, Qj. Okay, any two of them, and then the distance between them to be the distance between the charge I and charge J to be Rij. Okay, so here the summation is a little bit strange. Okay, so this is I is not equal to J. Okay, so which means that we not try to sweep through I and sweep through J. Okay, the idea here is like for example, if we have three charges, let's say okay, so suppose we have a Ij from 1, 2, and 3. Okay, suppose we have three charges. Okay, 1, 2, 3. Okay, so what we want to have is I is not equal to J, so we don't have this one, don't have this one, don't have this one. Yeah, but probably we also need to add another criterion is that I is smaller than J, so which means that I is larger than J, depending on what you like. If I is smaller than J, then so we have this one, and this one. Okay, so this one for I is smaller than J. Okay, because this one. Okay, let's say this one and this one should be the same. Okay, this one and this one should be the same, and this one and this one should be the same. Okay, so you only need to calculate the lower half triangle or the upper half triangle. You don't need to calculate all the 6 terms. Okay, you only need to calculate I mean the NC2 terms. Okay, I don't think you need the 2 here. Yeah, so here is the so you don't need the n choose 2. Okay, n choose 2. Okay, so all together we have n choose 2 terms. So okay, so actually n choose 2 terms is n times n minus 1 over 2. Okay, so if n is 3 times 2 over 2 is 3 times. Okay, something like this. Okay, so this is a simple example. So here it says 3-point charges held in fixed position by force that are not shown. What is the electric potential energy U of this system of charge, assuming D? Okay, so this is an equilateral triangle, and then with Q1, Q2, Q3 to be these 3 amount, and then Q to be 150 nanocoulomb. Okay, so U will be like U12 plus U23 plus U31, okay? Altogether have three terms, okay? If there are 4 charges, that will be 4 times 3 over 2, which is 6 terms rather than 4. Okay, so here we have K times Q1, Q2 over actually D, okay? All the distances are D. Okay, so Q2, Q3 over D plus Q3, Q1 over D. Okay, so finally K over Q, K over D, Q1, Q2 plus Q2, Q3 plus Q3, Q1. So K is 8.99 times 10 to the 9th power. And then D is this 12 centimeter. Okay, change it to SI unit is 0.12 meter. And then here, Q1, Q2. Q1 is 1Q, okay. Q, we just put it at the back. Q is 150 times 10 to the 9th, okay. So we might do once again, okay. You need to memorize the scientific prefix, okay. I have supplemented in the slides of chapter 22, so make sure you try to memorize all those scientific prefix. Okay, so we only need to have 1 times -4 plus -4 times 2, and then plus 2 times 1, okay. So this is it. So finally, -1.7 times 10 to -2 joule. Okay, so joule is the SI unit for the energy. Okay, so this is quite easy. Just let you know how to make use of this formula to calculate the total potential energy, electric potential energy stored in the multiple charge system. Okay, so here we have an other sample problem. So here it says an alpha particle, 2 protons, 2 neutrons, move into a stationary gold atoms. Okay, so with 79 protons and 118 neutrons. Okay, so passing through the electron region that surrounds the gold nucleus, like the shell, and head direct towards the nucleus. Okay, so which means that this alpha particle, okay, this alpha particle with 2 protons, 2 neutrons, actually starting from infinitely far away. Okay, and then moving this way. Okay, so it will try to move closer and closer. It should towards. Okay, don't ask how you can do that. Okay, just assume this charge is moving closer and closer to this gold nucleus, but actually they won't hit each other. Yeah, because there are very strong electromagnetic force repelling each other. Okay, so as much as this one getting closer and closer together, there will be because this is a very strong 79E. Okay, this is 2E. Okay, both of them are positive charge. Both of them are positive charge, so there will be Coulomb's force repelling each other, so that this alpha particle will decelerate until it stops and then return. Okay, so the idea here is the alpha particle slows until it momentarily stops when its center is at radial distance. Okay, it just tells you that the closest distance out here is this 9.23, again, femtometer. Okay, what is F? Okay, from the nuclear center. Then it moves back along its coming path. Okay, so blah, blah, blah. Okay, so because the gold nucleus is much more massive than the alpha particle, we can also assume that the gold nucleus does not move. Okay, yeah, because it's also need to satisfy something like the conservation of momentum, yeah, something like that. But yeah, we just ignore the movement of the gold nucleus because it is much heavier. So what is the kinetic energy Ki of the alpha particle when it is initially far away? Okay, we need to know Ki Ui. Okay, at this point it is a Kf Uf. Okay, so the kinetic energy for K and then the potential energy for U, okay? Okay, assume the only force acting between the alpha particle and gold nucleus is the or the Coulomb's force. Okay, so here we have the conservation of energy, conservation of mechanical energy. We don't assume there are any force, okay, because the question tells you that we assume only force acting on them are the Coulomb's force, okay. So we don't have any force to work on this system. So we have the conservation of mechanical energy. Okay, so initially this charge, okay, this alpha particle is far away, so Ui should be 0, okay, Ui should be 0. Ki is what we want to find, okay, Ki is what we want to find. Okay, so for the Kf, this is momentary stop, okay, so the kinetic energy is half of mv squared, so this is 0, okay, and then it is UF we will be able to find, yeah, because we know the distance, we know the charge, so we will be able to find Ki to be UF, which is K times 2E times that one is 79, okay, 79E over this R, like this. Okay, so which is 2 times 79 times 1.6 times 10 to minus 19 whole square, and then over, okay, so I forgot this K is 8.99 times 10 to the 9th power, so over R, 9.23 femtometer. 9.23 femto is 10 to minus 15. Okay, so this is 3.94 times 10 to negative 12 joule. Okay, actually this one is okay. Joule is a SI unit. Yeah, but for the particle physics, they usually use another unit, okay, called the EV. Okay, called the EV. Okay, so what is the relationship between EV and joule is 1 EV is actually 1.6 times 10 to minus 19 joule, okay? So this is the elementary charge, okay? So this is 1 EV, so which means that you need to use 1 EV of energy to accelerate a charge, okay? So or maybe changing its potential by 1 volt, okay? So this is the energy of 1 EV. So if you try to do that, you can actually represent it as a 24.6 mega EV. Okay, times 10 to the 6th power of EV. Okay, so the particle physics guy like something like the number larger than 1, okay, rather than this negative 12 power. Okay, so they would like to have a new numerical value like larger than 1. Okay, so use a much smaller unit to make it work, to make it happen. Okay, let me finish this graph and then this page, and then we can take a break. So finally, we talk about the potential of charge on isolated conductor. Actually, what we try to talk about is, actually, we already know that negative dV/dr is actually the E along the R axis. Okay, suppose the E field are all along the R. Okay, suppose it is a spherical coordinate with a single charge. So it will be like that. Here is other stuff we say that, okay, suppose this is a conductor, okay, this is a conductor, okay, and then as we have mentioned, okay, all the charge will go to the surface, and then inside the conductor there won't be any E field, okay, there won't be any E field. So which means that, okay, of course this is a car, suppose for a simplified case, we have a sphere, okay, all the charge are distributed on the surface, so that no E field inside. Okay, so E field are 0 inside, so we have a E field inside. But out of the sphere, this E field is proportional to 1 over R square. Okay, if you still remember. Okay, hopefully you remember because we have quiz next week. Okay, so which means that we know that dVdr will be E, but for this region is 0. So which means that the potential inside the car, or at least inside the sphere, is a constant. Okay, so it is flat, and outside the sphere we also have this one. Okay, this is proportional to 1 over R. Okay, proportional to 1 over R. Okay, so which means that we take the derivative. Okay, take the derivative of 1 over R square to become 1 over R square. Yeah, because of course we have a negative side, but we have another negative side, so to make it positive. Yeah, and then here is a constant, so which means that, and here is finite, so here it should be continuous. Okay, here it should be continuous. So this figure just want to tell you that as much as we have these two in relationship, or actually this one and this one are inverse to each other. This one and this one are actually inverse to each other, which means that okay, so actually we can have a v. Okay, to take the derivative, take a minus sign, we have e, or we can have a e dot ds. Okay, take the line integral and then take the minus sign to become this one. Okay, so just now I forgot to mention that why I mentioned the gradient theorem, because we have this one. Okay, we have this one. This one and this one are inverse operation to each other. So the gradient and this line integral are inverse to each other. Yeah, so going back to here, so it really means that, yeah, so it really means that, okay, so even though there are some lighting hitting the car, okay, hitting the car, so all the charge will go to the surface, and then the E field will not be 0 outside the car. So inside the car, the E field is 0, and then all the point with the same potential. So which means that this guy inside the car won't be harmed by this lightning. Okay, so it is wise to enclose yourself in a cavity inside the conducting shell. So where the electric field is guaranteed to be 0, a car, unless it is convertible made with a plastic body, is almost ideal. Okay, so which means that this guy is safe. This guy is safe. Or sometimes we will call this phenomenon the Faraday's cage. Faraday's cage. 法拉第电笼. Okay, so like this. Yeah, so